and good morning, everybody, to this first speech of this session. So, this work has been done in collaboration with the University of Rome, University of Trento, and University of Padua. I'm a postdoctoral fellow at La Sapienza University of Rome, and as mentioned, the work will be on the fatigue evaluation in between the continuous and pulsed wave laser powder bed fusion on lattice structures. Indeed, we are dealing with additive manufacturing, in particular metal additive manufacturing and architected cellular materials. Probably most of you know that this allows to build really complex structures in a simple manner and with tunable mechanical properties. Nonetheless, before the full width spreadability over different industrial fields, ranging from the biomedical to the aerospace one, there are still some concerns that hinders this spreadability, which are mainly associated to structural integrity issues and in particular to fatigue-related issues. These issues are mainly associated to the microstructure, but when we are dealing with additive manufacturing, also to process-induced defects, due to the fact that the technology is really complex, is a little bit difficult to be optimized and tunable in a consistent manner. These defects mainly related to the differences in between the as-built and as-designed geometries. And these encompass, for instance, enhanced surface roughness, parasitic masses, drosses at the lower skins. Given this, when we're dealing with metal additive manufacturing, most of the times we are talking about laser powder bed fusion, which is one of the most industrially ready technology. Nonetheless, also dealing with laser powder bed fusion, we have several sub-technologies. For instance, changing the way the laser is emitted can alter the overall melt pool dynamics and the overall generation of defects inside a component. Indeed, the laser emission can be, for instance, pulsed or continuous. As you can understand, if the overall melt pool dynamics changes, also the fatigue behavior might change. If we see this under an industrial perspective, usually an industry wants to have productivity, so optimizing the printing speed, at the same time dimensional accuracy, so a good defect density and sensitivity. At this point, you can understand that these requirements might be conflicting, and so optimization processes are needed in order to balance the quality over the cost. Nonetheless, in most of the cases, these optimizations overlook the fatigue reliability of the component. So the aim of this work is considering two industrially optimized set of parameters for two laser powder bed fusion technologies, continuous wave and pulsed wave, and considering Ti-6-4 lattices, we want to understand what is the fatigue behavior and if and how there are these changes. To do this, we decided to adopt a bottom-up approach rather than printing overall lattice components. We decided to use subunital elements, so the smallest repeating units that we have inside the lattice, which are not the units themselves, but the struts. Why this? The reason is twofold. First of all, there is, of course, a saving of money in order to print less specimens in higher number. And second of all, because fatigue is a localized damage phenomenon. And so if we understand how the failure occurs and how the fatigue properties are inside these specimens, then we can scale up to the overall lattice component. To do this, we designed some specimens, which we call thin struts, which mimic the struts of a lattice, at three different building orientations, 90, 45, and 15, with respect to the job plate, with a nominal strut diameter of 670 micrometers and overall gauge length of 2.4 millimeters. These specimens have been printed according to the before-mentioned manufacturing processes, considering some optimized parameters in order to balance the printing quality and the cost. Of course, if we want to have a comparison, we need to have something fixed or at least constrained in order to have the closest comparison as possible. And to do this, we decided to keep the same layer thickness, same feedstock powder, as well as comparable energy density per track width. Given this, these specimens should be considered in their as-built conditions, so any kind of post-processing treatment has been done, rather than a classical heat treatment to have either stress relieving, either the transformation change from martensitic to alpha plus beta phase. Given this, before going through the experimental campaign, it occurs to have an overall morphological analysis of the components. As I said, process-induced defects in fatigue are really important. So first of all, understanding the deviations that we have in between the as-designed and the as-built structure is really important. To do this, we performed a really fast and cost-effective stereoptical image analysis approach, which basically collects two images, one horizontal and one vertical image, so basically flipped of 90 degrees with respect to the horizontal image. And through some image processing analysis that has been done in MATLAB, but that can be extended to any other type of solver, we are able, with an assumption of an elliptical cross-section, to build up the cross-sectional data of each specimen over the gauge length, considering thus the average cross-section and the minimum cross-section. We decided to employ the minimum cross-section for the fatigue analysis, as you will see later. But most importantly, we can compare the overall initial, preliminary at least, results of the printing. As you can see, the pulsed wave and the continuous wave laser powder bed fusion do not have only differences in between the different angles within the same technology, but there are critical differences also with respect to each type of manufacturing technology. In particular, you can see that there is an overestimation of the cross-section in the case of pulsed wave laser powder bed fusion, while there is an underestimation of the cross-section with respect to the nominal values for the continuous wave laser powder bed fusion, which in other terms means that the load-bearing area for pulsed wave laser powder bed fusion is larger than for continuous wave laser powder bed fusion. As I said and anticipated, we are using the minimum cross-section for our data analysis on fatigue, and in particular, fatigue test has been done at R equal to -1 in mode 1, and these are the SN curves, Euler curves of the components for the pulsed wave and the continuous wave according to the 3 different building orientation. Why the choice of the minimum cross-section? Because in this way, we can already account for the differences that we have in terms of morphology, at least in a preliminary stage. If we would have used the nominal cross-section, we would have way larger discrepancies, which would have not account for this difference. So given this first look at these graphs, we can clearly say that the pulsed wave laser powder bed fusion reports higher fatigue strength with respect to the continuous wave laser powder bed fusion for any given building orientation. However, if we have a closer look at the different trends at fixed angles at 10 power, at fixed cycles, at 10 power 5 numbers of cycles, 10 power 6 and 10 power 7, we can clearly see that these trends tends to increase with the increase of the numbers of cycles. And particularly for the 90 degrees, there is a perfect match at 10 power 5, which instead tends to decrease with the increasing of the numbers of cycles. So why this? Can we explain these trends? And in order to do this, usually when we talk about fatigue and fatigue strength, we consider a function of the base material, of the architecture, and of the fabrication process. But if the base material is the same and the architecture is the same, this suggests us that the fabrication process is the key differences. And in particular, we are analyzing surface defects, porosity, and microstructure, which might be the driving phenomenon which leads to the failure. So starting with a surface roughness analysis that has been done on both cases for all the building orientations, we have basically 2 parameters of interest, which are the RA and the RV, as well as the SA and SV. And we can consistently see that there are differences, statistical significant differences, between the pulsed wave and continuous wave, particularly at inclined angles. However, when we are dealing with 90-degree specimens, we do not see any kind of statistical difference. This, if you remember the graphs before, suggests us that probably surface roughness is not the driving mechanisms that leads to the discrepancies in fatigue resistance in between the pulsed wave and the continuous wave laser powder bed fusion struts. So the other logical step is to go through the porosity analysis. Porosity analysis has been done basically cross-sectioning the specimens, several numbers of specimens, at different height of the gauge length in the Z direction, and considering then the Murakami area parameter on the XY direction, and considering the distance from surface and the circularity of the pores, we can see that in the case of pulsed wave laser powder bed fusion, there is a higher tendency for the 90 degrees in particular to have a location of potentially critical pores near the change in between the contour and the bulk part of the strut. This would suggest, preliminary, that this might be the driving mechanism. But if you remember the graphs before, basically it's flipped, because the pulsed wave laser powder bed fusion reports a higher fatigue strength with respect to the continuous wave. So again, probably this is not the mechanism. In this case, if we look at the 90 degrees case study, as I said, there is an increase in the fatigue strength difference with an increase of the numbers of cycles. And this cannot be explained neither by the surface roughness analysis, neither by the porosity. So mostly probable, it's related to the microstructure. How did we deal with that? We did some ABFD analysis of the 90 degree struts, and we checked basically the overall morphology. As you can already see, microstructure, sorry. As you can already see, there are clear differences that are evincible from these SCN images. And in particular, these differences are not related to the alpha grains, which are comparable in size and length, but are mainly related to the prior beta grain reconstruction. And in particular, you can see that for the pulsed wave, there are way larger grains with respect to the continuous wave laser powder bed fusion. But how does this impact on fatigue? The answer was given basically by literature and by a beautiful paper published in the International Journal of Plasticity in 2023 by the group of Sanjit on a crystal plasticity model on Ti-6Al-4V. And basically, the larger beta grains means also a lower density per volume of the boundaries of these grains. And so basically, this means that you can have a easier dislocation slip transfer, a less plasticity strain localization, which impact on a delayed crack initiation, and so impact on a higher fatigue strength. However, the nice thing about this is that it's also cyclic dependent, in the sense that this benefit is stronger the higher the fatigue life is, because we are in an initiation control domain rather than in a bulk plasticity domain, in which instead the plastic strain localization tends to be widespread more over the overall cross-section. Given this, we basically can explain, indeed, not only the differences that we have in between the continuous and the pulsed wave laser powder bed fusion struts at 10 power 6 and 10 power 7 cycles, but also explain why at 10 power 5 cycles we have a sort of perfect match of the fatigue properties. At this point, basically, just to conclude, given two optimized process parameters, which are aimed at balancing the cost versus the overall quality, we can say that with this set of parameters, which doesn't mean that for every conditions we have that the pulsed wave is better than the continuous wave, but for this set of parameters, we have that generally at any building orientation, we have a better fatigue strength for pulsed wave due to a higher cross-section, a lower surface roughness, and also a prior beta grain size, which is higher. So the chance, statistically chance, to have localization of plastic strain at the boundaries is reduced. Given this, just for future developments, of course, this is at the preliminary stage, we would like to extend this BSD analysis not only to the case of 90 degrees, but also to the case of 45 and 15 degrees, and then try to develop some quantitative model which accounts for both the combined effect of the microstructure and the surface defects. With this, and acknowledging the ERC project on which this work was founded, thank you very much.